Welcome to this explainer. Today, we're jumping right into a fascinating mathematical detective story. We're going to be exploring a framework called prime elementology, which was developed by researcher Fan Tentrung. We're looking at the very building blocks of our universe, atoms, but we're going to examine them through an entirely different lens. We're not talking about physical forces or quantum fields today. Instead, we're looking at the raw mathematics, the pure numbers that actually define these atomic structures.
Okay, let's dive into this. Every atom is defined by a set of core integers, right? The number of protons, the number of neutrons. But what if those raw numbers, those basic coordinates that we've literally used for decades, are actually more than just simple identifiers? What if the internal arithmetic of those numbers holds a hidden code? Almost like a structured mathematical language that artificial intelligence can read to predict exactly how stable an atom is.
Here is our roadmap for decoding this framework today. First, the standard nuclear identity. 2, the prime Ulam transformation. 3, testing the math. 4, randomized controls. 5, explainable AI and operators. And finally, number 6, a new scientific lens.
Section 1. The standard nuclear identity.
So in standard nuclear databases, an atom's identity is defined by a compact integer triplet, C equals Z, N, and A. Z is the proton number, N is the neutron number, and A is the mass number, which is just protons plus neutrons. Now, traditionally, in machine learning and physics databases, these three foundational integers are treated simply as raw index coordinates, basic numerical inputs. They're kind of like a zip code or a street address, just used to locate an atom on the chart of nuclides.
Now, what's really interesting here is the massive paradigm shift this represents. Standard models basically stop at the surface, using Z, N, and A just as raw numerical inputs. Prime elementology, on the other hand, treats these integers as structured arithmetic objects. It completely pivots from treating these numbers as basic variables to exploring their internal mathematical architecture. The framework asks a brilliant question. What if the way these numbers factorize actually encodes predictive regularities?
Section 2. The prime Ulam transformation.
So the framework uses a very strict chronological computational pipeline. Step 1 takes the raw identity, the protons, neutrons, and mass. Step 2 breaks those numbers down into their prime factorizations. Step 3 maps those numbers onto a geometric grid called an Ulam spiral. And finally, Step 4 feeds all of this rich, transformed mathematical data right into a machine learning model. It's essentially converting basic integers into a highly sophisticated, machine-readable mathematical language.
Think of prime numbers as the arithmetic DNA here. The framework calculates factor complexity, meaning how many prime factors make up the proton or neutron number. It looks at factor overlap. Do they share a greatest common divisor? And factor entropy. How is that prime exponent mass distributed? It is literally decoding the hidden mathematical overlaps and entropies existing inside the atom's raw numbers.
Then it adds visual geometry. Integers are mapped deterministically onto a 2D grid called an Ulam spiral. By plotting numbers in a spiraling square, the framework generates actual x and y coordinates for the protons, neutrons, and mass. This provides an absolutely brilliant geometric coordinate system. It allows the AI to measure the mathematical distance between an atom's protons and neutrons right on this spiral grid.
Section 3, testing the math. Now, a theory is really only as good as its predictive power, right? So the experimental design separates two entirely distinct data layers. On one side, we have real-world empirical nuclear data retrieved from the IAEA live chart. These are the actual observed atoms. On the other side, the author generated a massive mathematical candidate grid containing over 51,000 theoretical integer identities. The AI is then trained to classify which atoms are physically stable based purely on their math. And this brilliantly illustrates the massive leap in the AI's predictive power. Look at this. The M0 model, using just the raw identity, scored an F1 score of 0.6448. And remember, 1.0 is perfect accuracy. But when you combine that raw identity with the prime alarm descriptors, the score absolutely rockets up to 0.9298. By simply exposing the internal arithmetic of the numbers we already had, the AI became vastly more accurate at predicting physical atomic stability, no new physical data required. Section 4. Randomized controls.
Of course, we need sanity checks to ensure the AI isn't just hallucinating patterns out of pure statistical noise. So the author designed rigorous randomized controls. R1 shuffles the prime Ulam descriptors. R2 replaces the Ulam coordinates entirely with random geometry. R3 feeds the model matched random features, and R4 shuffles the prediction targets entirely. If the AI still scores highly on these, well, then our framework is just an illusion.
But the results here are incredibly validating. When the prime-ulam descriptors are column shuffled in the R1 control, which completely destroys the row-wise alignment of the math to the specific atom, the score absolutely tanks to 0.1994. This proves, without a doubt, that the specific mathematical alignment of an atom's unique protons and neutrons is exactly what drives the AI's success. It is not just benefiting from extra random data.
However, good science requires total honesty. So the crucial point is this specific number, 0.9062. You see the randomized Ulam control, R2, still scored a very high 0.9062. This means that while the overall framework is highly successful, the independent value of the deterministic Ulam geometric coordinates requires further scientific isolation. The high score implies the AI might just be using those coordinates for dimensional expansion, so we can't claim the Ulam spiral alone is the magic ingredient just yet.
Section 5. Explainable AI and operators.
Let's move to and see how this builds into actionable tools. Explainable AI here doesn't just look at a one-off feature ranking. Now, it relies on finding patterns that are consistently important. It demands what's called rank stability. The framework tracks which mathematical features, like factor overlap or entropy, repeatedly survive across multiple validation folds and random computer seeds. It only trusts the patterns that show up consistently.
Once those stable patterns are found, the framework performs a fascinating process called operatorization, which is really just a cool way of saying it turns these stable AI patterns into reusable computational tools for scientists. For example, the stability search operator ranks theoretical atoms to find new stable ones, while the residual reader highlights atoms where standard physics models leave unexplained errors, pointing researchers directly toward interesting anomalies they should study further.
Section 6. A new scientific lens.
Now, we definitely need to apply the brakes on the hype here. As the source material explicitly states, the framework does not claim that arithmetic descriptors replace nuclear theory, shell models, quantum mechanics, or empirical mass models. This is absolutely not a mystical claim about prime numbers physically holding atoms together. The primes are not a new fundamental force of nature, okay?
We really need to reinforce exactly what the benchmark supports, keeping the science completely realistic and rigorous. Prime Elementology is a brilliant computational data science tool. It provides a representational gain for machine learning. The Ulam coordinates are arithmetic tools. They are not a map of actual physical space inside the nucleus. The descriptors expose computational mathematical patterns. They absolutely do not establish physical causes.
So, to summarize our deep dive today, the core takeaway is this: transforming the basic integers of an atom into prime factorizations and arithmetic geometries provides a highly testable and incredibly powerful representational layer for modern AI. By simply looking deeper into the structure of the numbers we already use, we unlock a much richer vocabulary for machine learning models to understand the physical universe.
This whole explainer really highlights the profound intersection between pure mathematics, data science, and physics. I mean, think about it. If breaking down the raw proton and neutron counts of an atom into their prime factor DNA can suddenly yield a massive jump in predictive AI accuracy, it leaves us with one incredibly exciting thought. What other hidden numerical architectures are just waiting to be sequenced in the natural world around us? Keep questioning, keep learning, and thank you so much for exploring this with us today.